Good day, everyone. We're on a journey to try to pick a right logic for our situation. We might be thinking scientifically or computationally, or maybe we're dealing with data, and that can influence what kind of logic is good for our jobs. And so we're going to need some method to describe a logic and have it passed along to other people. We're headed to something called a calculus. In this case, it'll be a sequent calculus, a way of writing down which logics we want to communicate to each other, and a way to pass along operations, calculations that we might take place in these different logics. To get us started in that path, we're now going to take some of the words that we use when we describe logic and start to put symbols to them. This will make it reliable and transferable to, say, a computer, as well as some of our colleagues. So let's get started with the word of grammar. Suppose that I looked at the expression 8 times the quantity 7 plus 3 squared. I believe most of us would be able to work out the correct answer. We would start by taking 7 plus 3 and turning that into 10. Then we would square because it's inside of parentheses. So we would have 8 times 100, and then we would get that to be 800. These steps are correct. No surprises here. Now I want to try to expose how we might think of that grammar as a set of instructions. And for this, I'm going to use a picture. Here's a way to see all the data that's going on in this compact formula. We see, reading from left to right, that we have this natural look of a tree. Here in my tree, I see that I first took apart the multiplication. The reason to take apart multiplication is because it's the last thing we did in our project. The 8 times 100 appears as the last step in this tree. What's the first step we did? The first step was 7 plus 3, and that occurs at the bottom. So the way we read this tree is once we've built it, we go from the bottom up and evaluate each of the operations. First, we encounter 7 plus 3. We do that. That becomes 10. Then we find 10 squared. That replaces the 7 plus 3 squared with 100 and all the way down. It's a predictable set of steps. That's the key point of the grammar, is it breaks it up into a way that everybody can get to the same answer. It makes it clear what operations come next, and that order really matters. Notice that while there are operations that we can do in any order, for example, I can add in any order, I can't multiply and add in any order. That really changes the meaning. Here we had to add first and then multiply. So order does matter, and grammar lets us capture that. Let's see exactly how this looks. What we need is what's called a rooted tree. So here's one rooted tree, which just takes a formula of numbers, the way you would have think what we just did. But it's not just that. It can be sentences in logic. I could have something like and. This and that. That breaks up as two different parts. There's a this and a that. Together they become one new thing, this and that. We are now seeing that even logical frameworks become something like this tree. They're part of a grammar. And it even extends to things you might not expect, like the equal sign. If we think of the equal sign, on the one side we have a formula, we evaluate that till we get the number we need, and on the other side we can have a separate formula, and we only combine them at the end with the equals. Again, this is an operation gluing together some formulas, but it's written down using a grammar. The grammar helps us make sure that we use it in predictable ways. Let's quickly refresh what a rooted tree might be. Hopefully the pictures are giving you the best impression. That's usually what people need to study, but there is a way to describe it. A rooted tree has a root. We'll picture it up here as root. It also could be called a node or vertex. Each vertex can then have edges out of it. I've put arrows on here to emphasize that they left the root, but they have to go to new nodes. The key thing about new is to avoid unpredictable behavior. We'll see that evolving in several examples. Let's see it in a couple examples here. From this second new node, I've created another node and another node. This one I'll call a leaf because it has no further nodes. This node over here may or may not have other values, so it might not be a leaf of our tree. Here's what isn't allowed. I can't take this edge and connect it back to an existing node, like that. If I did that, I would violate this second rule. It's not a new node. And you can see what this starts to do. If I insert a path back to something I've already seen, now I can start to go in circles. It means that I don't have a predictable way to get from one point to another. It stops being unique. Our whole point is to explain ourselves so clearly that it's logical, meaning everyone could come to the same conclusions from the same context. This is why we don't want loops. We don't want to find ourselves in patterns that are difficult to explain. And so this leads us to our first main theorem. It's a major fact in the world of graphs that a tree has unique paths between any two vertices. In this case, any place that I call a leaf, a place with no further edges, can only trace back to the root in one way. We would have to go back and forth on some edges, reversing the order if we wanted to have different paths. So if we follow the order from the root to the tree, it gets there in exactly one way. The consequence is, if we write a grammar with something that's backed up by a rooted tree, then once people read this in this grammar, they will understand exactly what we intended. We will all, now, past and present, will all get the next point of the tree exactly the same place. We'll come up with the same understanding of the formula. That's the key reason to want this. The kinds of grammars we're going to work with are so basic that you can write them down with a few lines sometimes. Here's an illustration. What I've done here is I've written subject as a key word, and then I've assigned it a value, Jack. But it's not the only way I can get the subject. I'm also allowing myself to have Jill. This goofy double colon equals is just to emphasize that this is assigning the value Jack to being a subject, just like Jill. Modifier could be up or it could be down. And the objects in my grammar are hill and river. Now, a sentence in this grammar I've listed as sentence. This double bracket is to emphasize that that's the end of the story. My whole goal was to design what sentences are allowed in this grammar. And my sentences must have the following structure. They must start with a subject. Then they include the word went. Then they must have a modifier, then the word the, and then one of the objects. Let's see what that would mean. Here's a sentence that's called well-formed, meaning the grammar accepts this as a valid sentence. I've put in green the various values that are optional. Jack went up the hill. We see that Jack is a subject in the right place. Went is in our sentence. Modifier up is allowed, the is allowed, and then the object hill. Another sentence might be Jill went down the river. We've simply modified what values are in green, but went and the are in the same place. This might not seem like mathematics, but notice if I replace these with symbols like plus and times, you would now see that's the way we write formulas in mathematics. X times Y plus Z is another type of grammar. It's just using different symbols instead of words. Once you break it down to this understanding, you'll connect many worlds in your thinking. There are sentences that we don't allow in grammars. For example, Hill went Jack the up. It doesn't even sound like a sentence, but that's not what doesn't count here. What counts here is that our format required subject first, and that was only Jack and Jill. Hill is not one of those. And Jack is not a modifier, so it doesn't belong there. So here's some jargon that you'll hear in the general discussion of grammars. We'll talk about parsing. Parsing is taking a sentence, running it through the grammar, and deciding if it's well formed, meaning it passes all the rules of the grammar. When that happens, we create a tree to go with it. That tree is sometimes called the parse tree or the abstract syntax tree. That's jargon that I won't use very much, but you might hear it when looking around. The notation that we're using with these goofy angle brackets and double colon equals, this goes back to a famous work of Backus-Naur. It's now called the BNF, or Backus-Naur normal form. It is an important thing in a lot of the sciences and computer sciences especially. It's also in the background of many things that you might have done on the passive level, like writing some code. So now let's get to something that's a little bit more efficient. Notice that we had to repeat ourselves with these subjects. At some point, we get tired of typing that much, and we allow ourselves to combine some steps. So now we'll just separate the options by this vertical pipe. We do this to say that this could be Jack or Jill. And then up and down, we might write them in a stack. We're not required to glue them together, so you can see that there are many options, like hill and river are still treated separately, but it's the same meaning as having them combined by that. This is just a shorthand notation that I'll use so that this little middle digit is now in there. It was missing in my previous version. What this allows then is that the number 1 as a digit is accepted as a natural number as well. It's right here, it's one of the options. So I'm allowed to say 1 is a digit, so it's also a natural number. Now that we know 1 is a natural number, it can be used right there, which means it can be preceded by any digit. We see 4 is a digit, so therefore 1 is allowed. Therefore 41 is a natural number. Can you see why 541 would be a natural number? Again, once 41 is a natural number, it can be used here. And now we can fetch any digit, of which 5 is a digit, so 541 is now a natural number. That's how this process goes. Now this is a pretty straightforward grammar. They do get messier than this, but they're also, in the world of mathematics, often about this level of complexity. You list a bunch of constants that must appear in some order, and you put the operations between them the way you want them to see. Let's see what happens if we try to do this with negatives. Our negatives are not accepted right now because we don't have a minus sign in front of any of our digits. So therefore, negative 541 is not showing up as one of the arguments that's accepted. It's rejected technically. So let's add it. What we see is that we can put an extra case and call this a new thing called int, integer. Now there's a goofy letter Z here. This comes from the German word that's often used for integers. It starts with the letter Z. And mathematicians like to keep that pattern and use the letter Z and let the letter N be the positive integers. In computer programming, you'll see it as int or maybe integer, and maybe it'll be capitalized or lowercase. However you encounter this, it's usually pretty predictable. The minus sign here now allows me to predict that negative 541 is allowed. And so my notation could be saying, I could either say it in English, accepts negative 541, or I could write it with notation, negative 541 colon int, that says it's accepted. Or another notation would be negative 541 colon Z, if you prefer this mathematics notation. A little word of warning. I'm not going into a deep dive into grammars and all the various things that we have to do beyond that. So for example, in this grammar, I've permitted negative 0 to appear here. But we also know that negative 0 is also equal to 0, and so it could have appeared here as well. So there's two ways to get the 0 into our system. It appears as negative 0 and 0. And as it stands, there's no reason for the computer to know those are the same. This is the nuance. Grammar doesn't do everything we need logic to do, but it does quite a bit. And there are ways to fix it, but they're really not our course. So we'll leave it at that. So here's some notation that we've seen while we were driving by. If you're programming, be prepared to see words like int with a space and then some content, some data, a variable, something that you need to look up. It might also be written as that data colon int. These are both common notations and they're both specifying the same thing. They're saying that the data you've encountered satisfies the rules of that grammar and later the rules of that data type. Grammars give us one type of data type. So it's a preview into that giant world of programming. In mathematics and in computation, it's common to see a colon between the type, the Z in this case for integers, and the data. Now in mathematics exclusively and in some of the sciences, we change that colon for this symbol E. It's pronounced element of or simply in, and it has a slightly different role. We'll get into that when we look at sets. So technically there's not an equivalence between these two, but they're very closely related. So if I use one or the other, or someone around you uses the other, assume that they could have meant either one. You'll probably be safe. Now let's bump up to something stronger like polynomials. Here's a grammar that could describe something like a formula in mathematics. I won't go through how we write natural numbers. We already did that on a previous slide. And to get decimal numbers is slightly more work, but also can be done. What I want to do now is add some operations like pluses and times and some variables. So I've created a new variable value. It could be x, y, or z. You might add other names to that, but I'm being simple-minded here. My polynomial can either be a decimal number, or it can be a variable, or I can add two existing polynomials, multiply two existing polynomials, or take a polynomial and raise it to a positive integer. These are the ways that I can create a polynomial. Now again, this is written in such a simple way that it will never be misunderstood, but it's not exactly how humans like to write things. Here's an example. This sentence accepted 3.14 because that was allowed to be a decimal. And once a decimal is allowed to be a polynomial, then I can add a polynomial to anything else that's a polynomial. And x caret 2 is a polynomial. That's the bottom line. However, notice that's not the same as raising x to the power 2 in the notation we might do on a chalkboard. Now, this is simply because on a keyboard, I don't have easy ways to make exponents. So I want this to be accepted by, say, my calculator or computer. So I'm changing the way I might naturally do something as a human to write it for a computer. Likewise here, I'm not allowed to abbreviate 2 times z as 2z, which we might do amongst friends, but the computer will be hesitant to accept that. Now, there are ways to fix this, but this is just to point out that if you're trying to make something very clear, you might go for something slightly weaker than a human would ask between each other. Keep that in mind. As we come to the end here, there's a technical word that I should tell you so in case you hear other people talking about this. Everything we've done is a very specific kind of grammar. It's known as a context-free grammar. That's part of something called the Chomsky hierarchy that studies languages in general, and it's used by linguists all the way down to computer scientists and mathematicians in between. The key thing I want you to know is that this does not capture grammar in the way that natural languages are built. Take the sentence, algebra students love or hate grammar. To explain that to ourselves, we end up splitting our data of love and hate along a loop. It sort of doesn't describe everything as a tree in the way that we might naturally do. Now, this can be fixed, but it points out that the way we think of grammar is much more complicated and nuanced when we use human language, natural language. And whether natural languages, even like English, are context-free is a huge debate that people go back and forth on. You can see the work of James Higginbotham to sort of analyze the different arguments. I won't get into that fray. I just want to say that when we're talking arguments in logic, we are saying to ourselves, we are going to take away some of the natural language because that leads to confusing, sometimes circular arguments. We're going to try to hesitate and put in more symbolic arguments, symbols in pure logic that look like the trees we've seen on the previous page. The whole reason? Every grammar that we will encounter for logic can be translated into these rooted trees. So that's enough. And once we have a rooted tree, the feature of that is that there's a unique way to get from the root to every leaf. So no one can misunderstand what we're trying to say. That's the point of putting a grammar here. If you move to natural language, accept the circumstances might lead you into circular reasoning. Until next time.